Imagine a reality where particles flicker in and out of existence, where an object can be in two places at once, and where the mere act of observation can alter the course of events. This is the strange and mind-bending world of quantum mechanics, a realm that defies intuition and rewrites the very fabric of reality. At the heart of this mysterious science lies a truth more perplexing than fiction. Electrons behave as both particles and waves. Entangled particles communicate instantaneously across vast distances, and the universe itself may be shaped by the observer's consciousness. But what if this connection goes even deeper? Some scientists and philosophers propose that quantum mechanics might hold the key to understanding consciousness itself. Could the brain operate on quantum principles? Theories like OR, orchestrated objective reduction, suggest that consciousness emerges from quantum processes within the microtubules of brain cells, blurring the line between the mind and the fundamental workings of the universe. If true, this could mean that our thoughts, choices, and even our perception of reality are linked to the quantum fabric of existence. Yet, beyond the equations and experiments, one question lingers, one that challenges the very nature of existence. If reality is shaped by observation, then what role does consciousness truly play? Could it be that the mind is not just a passive spectator, but an intrinsic part of the quantum dance of the cosmos? Chapter 1: Foundations of Quantum Mechanics and the Observer Effect. For centuries, science has sought to answer the fundamental question: what is reality made of? From the ancient philosophers of Greece and India to the pioneers of classical physics, the world was believed to function like a machine, a deterministic system where every effect followed a cause with absolute precision. A simple example of a deterministic outcome is dropping a ball from a height. When you release the ball, gravity pulls it downward and it will inevitably fall to the ground. The effect, the ball hitting the ground, is entirely determined by the cause, dropping the ball from a height, and the laws of physics. Regardless of how many times you repeat the experiment under identical conditions, the outcome will always be the same: cause and effect in action. This view persisted until the dawn of the 20th century, when the emergence of quantum mechanics shattered the very foundation of our understanding. Quantum mechanics is unlike any scientific revolution before it. It challenges our intuition at every level, revealing a world where particles can exist in multiple places at once, where observing something can change its nature, and where objects can be instantly connected across vast distances. At the heart of these mysteries lies the observer effect, a phenomenon that suggests measurement, perhaps even consciousness itself, plays a fundamental role in shaping reality. This chapter explores the evolution of quantum mechanics, the perplexing wave-particle duality, and the controversial measurement problem, a puzzle that physicists and philosophers alike have struggled to unravel. Is reality independent of the observer, or does consciousness itself determine existence? For over 200 years, classical mechanics, based on Newton's laws of motion, provided a complete and predictable model of the universe. The behavior of planets, projectiles, and even fluids could be calculated with absolute certainty, leading many scientists to believe that the universe was a clockwork machine, obeying strict deterministic rules. This concept was reinforced by Pierre-Simon Laplace, who famously proposed that if a hypothetical Laplace's demon possessed complete knowledge of the position and momentum of every particle in the universe, it could precisely determine both the past and the future. According to this view, free will was merely an illusion, and the universe operated with strict mathematical determinism. However, as scientists explored deeper into the atomic and subatomic domains, cracks began to emerge in this classical perspective. By the late 19th century, various experimental anomalies indicated that Newtonian physics was insufficient to fully explain nature's workings. These inconsistencies set the stage for the most profound scientific transformation since Galileo, the advent of quantum mechanics. The quantum revolution, Planck, Einstein, and the birth of the photon. The first major challenge to classical physics came from Max Planck, a German physicist studying the radiation emitted by heated objects. The ultraviolet catastrophe and Planck's quantum hypothesis. Classical physics predicted that a heated object should emit infinite energy at high frequencies, leading to what was called the ultraviolet catastrophe. This prediction arose from the equations of classical electromagnetism, which suggested that objects should radiate increasing amounts of energy as the frequency of emitted light increased, eventually leading to an impossible infinite energy output. However, experimental results did not match this prediction. Instead, the observed radiation from hot objects followed a different pattern, one that classical physics could not explain. To resolve this, Planck made a radical assumption. Energy is not emitted continuously, but in discrete packets called quanta. The energy of each quantum is directly proportional to its frequency, meaning that higher frequency radiation carries more energy. This was an entirely new way of thinking about energy, contradicting the classical assumption that energy changes smoothly. Although Planck himself initially believed this was just a mathematical trick, his discovery laid the foundation for quantum mechanics. Einstein and the photoelectric effect, proving light is a particle. A few years later, Albert Einstein expanded on Planck's work to explain a puzzling phenomenon called the photoelectric effect, the emission of electrons when light strikes a metal surface. In a typical photoelectric experiment, a beam of light is directed at a metal surface, and the ejected electrons are measured. The light can vary in both frequency, color, which determines the energy of each photon, and intensity, brightness, which affects the number of electrons ejected. The experiment aims to observe whether or not the light causes the metal's electrons to be ejected, and how the frequency and intensity of the light affect the result. Classical physics predicted that increasing the intensity or brightness of light should always increase the number of emitted electrons. It viewed light as a continuous wave, where higher intensity meant more energy distributed across the wavefront, allowing electrons to gradually absorb enough energy to be ejected from the material over time. However, Einstein's experimental results showed something completely different. One, if the light's frequency was too low, no electrons were ejected, no matter how intense the light was. This means that even if a strong beam of low-frequency light continuously shined on the metal, it could not free any electrons. The electrons in the metal are bound within its atomic structure, particularly in the outermost layer, known as the valence shell. To escape, an electron must absorb enough energy to overcome the attractive forces holding it within the metal. This minimum required energy is known as the work function. If the incoming light has a frequency too low, and thus its photons have too little energy, no single photon can provide enough energy to free an electron. Even if the light is extremely bright, it simply bombards the metal with more low-energy photons, none of which are individually strong enough to knock an electron loose. 2. Electrons were ejected instantly when exposed to high-frequency light, even if the intensity was low. As soon as a single photon with enough energy strikes an electron, the electron is ejected immediately, without any delay. Unlike a wave that gradually transfers energy, photons transfer their energy in one instant. If a photon carries more energy than the work function, the extra energy is converted into the kinetic energy of the ejected electron. 3. The energy of the ejected electrons depended on light's frequency, not its brightness. Increasing the brightness, intensity of light only increases the number of photons hitting the metal, meaning more electrons can be ejected. However, the energy of each ejected electron depends only on the frequency of the incoming photons. A high-frequency photon results in a high-energy electron, while a lower-frequency photon, even at high intensity, cannot eject an electron at all. To explain these observations, Einstein made a bold proposal. Light is not just a wave. It is made up of tiny, discrete particles of energy, called photons. This was a revolutionary idea. Light had always been considered a wave, yet now Einstein was suggesting that it also behaved as a particle. His discovery earned him the Nobel Prize in 1921. and more importantly, it introduced one of the biggest mysteries in modern physics: the mystery of wave-particle duality. Einstein's work proved that light behaves as a particle when it interacts with matter, but earlier experiments, such as Young's double-slit experiment, showed that light also behaves as a wave, creating interference patterns. This contradiction, where light sometimes acts like a wave and sometimes like a particle, became known as wave-particle duality. If light could exhibit both wave-like and particle-like behavior, could matter do the same? This question set the stage for one of the most groundbreaking experiments in physics, the double-slit experiment. The double-slit experiment, the strangest experiment in physics. The double-slit experiment is perhaps the most mysterious and groundbreaking experiment in quantum physics. It not only challenges our classical understanding of the physical world, but also raises profound questions about the role of observation and consciousness in shaping reality. The experiment was first conducted with light, but when extended to electrons and even larger particles, it revealed something so astonishing that it continues to puzzle scientists and philosophers to this day. Wave or particle, the mystery of light and matter. To understand this experiment, imagine a simple setup. A beam of light is directed toward a barrier with two parallel slits, allowing the light to pass through. On the other side, a screen records where the light lands after passing through the slits. At first, we expect to see two distinct bright spots on the screen, one for each slit, if light behaves as a particle, like tiny bullets passing through separate openings. However, if light is a wave, it should behave differently. Waves overlap and interfere with each other. If light travels through both slits simultaneously, the waves can either reinforce each other, bright bands, or cancel each other out, dark bands. The result should be a wave-like interference pattern on the screen, with alternating bright and dark bands. The first surprise: light behaves like a wave. When scientists conducted the experiment, they did not see two bright spots. Instead, they observed an interference pattern, proving that light behaves like a wave. This was a significant discovery, confirming that light could spread out, overlap, and interact like ripples on a pond. But the real shock came when scientists repeated the experiment, not with light, but with electrons. Electrons, particles acting like waves? Electrons are tiny particles of matter. Classical physics predicted that electrons, being solid objects, should behave like tiny bullets. If fired one at a time at the double-slit barrier, each electron should pass through either one slit or the other. Over time, they should form two distinct bands on the screen, just like tiny pellets hitting a wall. However, the actual results defied logic. When electrons were sent one by one, they still formed an interference pattern, just like waves. This suggested that each electron was not traveling through a single slit. Instead, it seemed to pass through both slits at the same time, interfering with itself like a wave. This was impossible, according to classical intuition. How could a single electron go through both slits at once? Scientists realized that, at the quantum level, electrons did not behave like solid particles, but instead existed in a strange state known as superposition, a quantum state where they could be in multiple places at once. The act of measurement changes reality. To make sense of this bizarre behavior, physicists decided to take a closer look. They placed a detector at the slits to observe which slit each electron actually passed through. But something astonishing happened. The moment they measured which slit the electron traveled through, the interference pattern disappeared. Instead of behaving like a wave, the electrons started acting like particles, forming two distinct bands on the screen, exactly as expected from tiny solid objects. This meant that the mere act of observation changed the outcome of the experiment. The quantum measurement problem: does consciousness play a role? The double-slit experiment revealed something deeply unsettling. Before measurement, electrons exist in a superposition, traveling through both slits at once like a wave. After measurement, the superposition collapses and the electron behaves like a solid particle, passing through one slit or the other. But what exactly constitutes measurement? Is it simply interacting with a measuring device, or does it require conscious awareness? Does the universe exist in a probabilistic state until it is observed? These questions go beyond physics and touch on the nature of reality itself. Some physicists, like Eugene Wigner, propose that consciousness might be responsible for collapsing the wave function, suggesting that the physical world is shaped by the mind observing it. Others, like those who support the Copenhagen interpretation, argue that any interaction with a measuring device forces the quantum system to choose a definite state. Yet another idea, the many worlds interpretation, suggests that all possible outcomes exist simultaneously in parallel universes, meaning that in some universe, the electron went through the left slit, and in another, it went through the right. Conclusion: the mystery of reality. The double-slit experiment is one of the most powerful demonstrations of wave-particle duality, showing that matter and energy do not behave in an intuitive way at the quantum level. More importantly, it suggests that observation itself influences physical reality. Does this mean consciousness plays a fundamental role in shaping the universe? Or is measurement simply an interaction between quantum particles? These questions remain open, making the double-slit experiment one of the greatest mysteries in modern physics, a mystery that continues to challenge our understanding of the universe. At the core of this lies one of the most perplexing concepts, the wave function. Unlike classical physics, where objects have well-defined positions and velocities at all times, quantum mechanics suggests that particles, such as electrons, exist in multiple states simultaneously until they are observed. But what exactly is the wave function? The wave function is a mathematical expression that represents all possible states a particle can occupy. Rather than pinpointing the exact location of a particle, it provides the probability of finding it in different locations or states upon measurement. Before measurement, an electron does not possess a single definite position. It exists in a superposition of all possible positions. After measurement, the wave function collapses, meaning the electron is found in one specific location. This concept leads to a profound question. What triggers wave function collapse? Physicists have debated for decades about what causes the wave function to collapse, transforming a spread-out probability distribution into a single, definite reality. Several interpretations attempt to explain this phenomenon. One, the Copenhagen interpretation, Niels Bohr and Werner Heisenberg, the most widely accepted interpretation of quantum mechanics. It states that a particle does not have a definite state until it is measured. Before observation, an electron exists as a cloud of probabilities. The moment it is measured, the wave function collapses, and the electron chooses a definite state. 2. The von Neumann-Wigner interpretation. Does consciousness cause collapse? Proposed by physicists John von Neumann and later expanded by Eugene Wigner, this idea suggests that consciousness itself collapses the wave function. According to this perspective, physical reality remains in a state of uncertainty until a conscious observer perceives it. This interpretation raises deep philosophical and scientific questions. Is the act of measurement alone enough to collapse the wave function, or does a conscious observer need to be involved? Could this imply that human awareness directly influences reality at a fundamental level? 3. The many worlds interpretation, infinite realities. Proposed by Hugh Everett in 1957, this interpretation suggests that the wave function never collapses. Instead, reality splits into multiple parallel universes where each possible outcome occurs. For instance, if an electron has two possible paths, the universe branches into two. In one universe, the electron follows path A. In another, it follows path B. This theory eliminates the need for wave function collapse, but implies that an infinite number of realities exist. 4. Quantum decoherence, the role of the environment. The decoherence theory proposes that wave function collapse is an illusion, caused by a particle interacting with its surroundings. According to this view, when a quantum system, such as an electron, interacts with the environment, it loses its quantum coherence, making it appear as though its wave function has collapsed. However, in reality, the quantum system still exists in multiple states. It simply becomes impossible to observe due to environmental interference. The link between consciousness and quantum mechanics. The mystery of wave function collapse remains unsolved, and some physicists and neuroscientists suggest that consciousness may play a fundamental role in quantum mechanics. Could human observation actively shape the physical world as Wigner proposed? Or is the universe deterministic, with quantum probabilities merely reflecting our limited knowledge? If the many worlds interpretation is correct, does this imply that every possible version of our lives unfolds in parallel universes? These questions challenge the boundaries between physics and philosophy, making the nature of quantum reality one of the greatest enigmas of modern science. Quantum mechanics and the metaphysics of consciousness. Did the universe emerge from supreme awareness? The fundamental mysteries of quantum mechanics, wave-particle duality, the observer effect, and wave function collapse, not only challenge our understanding of reality, but also open the door to profound metaphysical questions. Could these strange phenomena hint at a deeper truth, that the universe itself emerged from a supreme consciousness? For centuries, spiritual traditions, particularly in Hinduism, Buddhism, and various mystical schools of thought, have proposed that consciousness is not a byproduct of the physical universe, but its very foundation. Modern physics, particularly quantum mechanics, seems to point in a similar direction. Wave-particle duality, the universe as pure potential until observed. In the famous double-slit experiment, light and matter exhibit both wave-like and particle-like behavior. Before measurement, a particle exists in a superposition of all possible states. It is everywhere and nowhere at once. Only when observed does it choose a definite state. This suggests that reality does not exist in a definite form until it is observed. But if this is true at the quantum level, could it also be true at a cosmic level? This leads to a profound question. If the universe itself was once in an undefined quantum state, an infinite sea of probabilities, what was the first observer that caused it to take form? If measurement collapses the wave function and brings reality into existence, then could the universe itself have required an observer to transition from potentiality to actuality? Many ancient philosophies describe the cosmos as emerging from pure, unconditioned consciousness. This aligns remarkably with the idea that the universe was once a field of probabilistic potential, much like an uncollapsed wave function, until it was perceived into existence. In Hindu philosophy, this primordial observer is referred to as Brahman, the ultimate, infinite consciousness from which everything emerges. The Rig Veda describes creation as arising from a state of pure formlessness, a condition similar to the undefined quantum superposition before measurement. The observer effect, consciousness as the creator of reality. The observer effect in quantum mechanics suggests that a system remains in an indeterminate state until it is measured. In other words, the act of observation is not passive, it actively shapes reality. This aligns with the idea in many spiritual traditions that consciousness is not just an observer of the universe, it is the very force that brings it into being. Consider the teachings of Advaita Vedanta, which state, the physical world is a projection of consciousness. Reality is not external but arises from the act of perception itself. The observer and the observed are ultimately one. These ideas are echoed in the Upanishads, which state, the universe rests within consciousness, as waves rest within the ocean. Consciousness alone is real, the world is its play. This is strikingly similar to the implications of quantum physics, where a quantum system does not take on definite properties until it is observed. The universe as a manifestation of supreme consciousness. If we consider the implications of quantum mechanics alongside ancient metaphysical thought, a profound idea emerges. Before the universe existed, There was only a vast, infinite field of pure potential, pure consciousness. This consciousness observed itself, causing reality to manifest, much like the wave function collapses upon measurement. The universe, then, is not separate from consciousness. It is a projection of it, much like a dream arising in the mind of a dreamer. This idea finds strong parallels in both modern physics and ancient wisdom. The Hindu concept of Maya, illusion, suggests that the physical world is a projection of a deeper unseen reality, similar to how quantum superpositions exist beyond direct perception. In Buddhism, the idea that form is emptiness and emptiness is form aligns with the notion that particles exist only as probability waves until observed. The supreme observer, the cosmic consciousness that brought reality into being. If wave function collapse depends on observation, and observation itself plays a fundamental role in shaping reality, then this raises a final profound question. Who or what made the first observation? Did consciousness precede the physical universe? Is our awareness a fragment of a greater, all-encompassing cosmic mind? Many religious and spiritual traditions suggest that the first observer, the supreme consciousness, is what we call Brahman, the Absolute, or the Divine Creator. This aligns with the Nasadiya Sukta, creation hymn of the Rig Veda, which suggests that before time and space, there was only an unfathomable awareness from which all things emerged. In the beginning, there was neither existence nor non-existence. There was only that one, breathing without breath by its own power. This could be interpreted as a poetic description of a universe existing in a quantum superposition before being brought into definite reality by the first act of observation, the first collapse of the cosmic wave function. Conclusion: consciousness as the foundation of reality. Quantum mechanics, rather than disproving ancient wisdom, seems to reaffirm the idea that consciousness is fundamental to reality. The wave function, the observer effect, and the indeterminate nature of quantum systems all hint at a universe that may not be an objective, mind-independent structure, but rather a consciousness-based reality. Could it be that the supreme observer, the ultimate consciousness, is what we call Brahman, the cosmic mind, or the divine? If so, then perhaps quantum mechanics is not just the study of particles and waves, but a doorway to understanding the nature of existence itself. A reality where the observer, the observed, and the act of observation are all one and the same. Chapter 2: Quantum Entanglement and the Nature of Reality. Quantum mechanics continuously challenges our classical intuitions about how the world works, especially through phenomena like quantum entanglement. Among the most perplexing and fascinating aspects of this field, quantum entanglement has ignited debates not only in the scientific community, but also in the realms of philosophy and consciousness studies. The concept that particles can instantaneously affect one another, regardless of the distance between them, seems to violate the very laws of space and time as we understand them. Einstein's spooky action at a distance. The term spooky action at a distance was coined by Albert Einstein in the 1930s to describe the strange behavior he observed in quantum entanglement. The crux of Einstein's objection to quantum mechanics lay in entanglement, where two particles, once interacting, remain correlated in such a way that any measurement performed on one particle will instantaneously determine the state of the other, regardless of how far apart they are. This was, for Einstein, an affront to the principles of locality and causality that were central to classical physics. According to relativity, no information or effect can travel faster than the speed of light. But in quantum mechanics, entangled particles appear to communicate instantaneously across vast distances, suggesting that the rules of space and time might not apply at the quantum level. Einstein famously referred to this phenomenon as spooky, underscoring his belief that quantum mechanics must be incomplete. He believed there must be some hidden variables, undiscovered mechanisms, that explain the seemingly inexplicable connections between entangled particles. In other words, he argued that the behavior of particles wasn't truly random. Instead, there must be some underlying factors, hidden variables, that determine the particle's behavior, but these factors had yet to be discovered. This stance was in contrast to the mainstream interpretation of quantum mechanics, which suggested that the behavior of particles is fundamentally probabilistic, with no hidden variables dictating the outcomes. Hidden variables theory. The hidden variables theory posits that the seemingly random and probabilistic behavior of quantum particles is not truly random. Instead, it suggests that there are unobserved factors, or hidden variables, influencing the behavior of quantum systems. In essence, the theory argues that the results of quantum measurements are determined by these hidden factors, which, if known, could provide a deterministic explanation of particle behavior. Einstein was a proponent of this theory, believing that quantum mechanics was incomplete and that there must be hidden variables underlying the observed phenomena. The hidden variables theory challenges the core principles of quantum mechanics, particularly the idea of wave function collapse and the probabilistic nature of quantum states. However, in the 1960s, physicist John Bell formulated Bell's theorem, which would have far-reaching implications for the hidden variables theory. John Bell came up with a clever way to test whether hidden variables could actually explain the strange behavior of entangled particles. Bell's inequality, the test. Bell's theorem came up with a mathematical equation called Bell's inequality, which provided a way to test whether quantum mechanics was correct or if hidden variables were to blame for the behavior of entangled particles. In simple terms, what Bell's inequality does is create a prediction about the correlation between measurements made on two entangled particles based on whether or not hidden variables exist. If the particle's behavior could be explained by hidden variables, the correlation between measurements would follow certain rules. These rules are defined by Bell's inequality. However, if quantum mechanics is correct, then the particles will behave in a way that violates Bell's inequality. In other words, quantum mechanics predicts a correlation between entangled particles that's stronger than what hidden variable theories could explain. What happens in the experiment? Bell's inequality was tested through experiments involving entangled particles. In these experiments, scientists measured the properties of two entangled particles, like their spin or polarization, at the same time. According to hidden variables theory, the correlation between these measurements should follow Bell's inequality. But quantum mechanics predicts that the entangled particles will violate this inequality. After testing this with real experiments, especially in the 1970s by physicist Alain Aspect and his team, the results showed that the behavior of entangled particles did violate Bell's inequality. This means that the correlation between the measurements was much stronger than what hidden variables could explain. The implication of Bell's theorem. So, what does this all mean? Bell's theorem proved that no hidden variable theory could explain the results of quantum mechanics. In other words, the strange instantaneous connection between entangled particles, what Einstein called spooky action at a distance, cannot be explained by any hidden factors that are local, meaning they don't communicate faster than light. The violation of Bell's inequality shows that entangled particles behave in a way that cannot be explained by any theory based on hidden, predetermined variables. Instead, quantum mechanics suggests that the particles are interconnected in a way that goes beyond space and time as we understand them. These particles seem to know what is happening to each other, no matter how far apart they are, and the behavior of one particle can instantaneously affect the other. This is a non-local effect, and it defies our classical ideas about how the world should work. Why is this so important? The result of these experiments was a monumental confirmation of quantum mechanics. It showed that the world of quantum particles operates in a way that challenges the ideas of space, time, and causality that we rely on in our everyday lives. Entangled particles don't seem to follow the rules of classical physics. Instead, they reveal a deeper, interconnected reality where space and time no longer have the same meaning as they do in the macroscopic world. Before we discuss what all this means for consciousness, let's first see what locality and non-locality mean in the quantum world. Locality is the principle that objects or particles can influence each other only through direct interactions within their immediate surroundings. This means information cannot travel faster than the speed of light, as dictated by Einstein's theory of relativity. Causal effects must propagate through space in a continuous manner, meaning there is no instantaneous action at a distance. For example, in classical physics, when two billiard balls collide, the second ball moves only because it was physically struck by the first. This effect is local because it occurs at a specific location and follows a clear cause and effect relationship. Non-locality, on the other hand, refers to the idea that particles can be instantaneously connected, no matter how far apart they are, without any direct or physical interaction between them. What does this mean for consciousness? This idea of non-locality, where things can be instantaneously connected across space and time, has some fascinating implications. Some researchers wonder whether human consciousness could also be non-local, potentially connected to a broader field of awareness that transcends our physical bodies and brains. Could our thoughts, perceptions, and awareness be linked to the universe in a similar way that entangled particles are connected? Could consciousness be fundamentally entangled with the universe? If consciousness follows quantum principles, it could mean that our awareness isn't just limited to our physical brains, but could be connected to the entire cosmos in a deep, quantum way. These possibilities suggest that the quantum nature of reality could be more than just a physical phenomenon. It could also offer a way to understand how consciousness itself works. Chapter 3. The Brain as a Quantum System. The human brain is the most complex known structure in the universe, capable of perception, memory, creativity, and self-awareness. For decades, neuroscientists have approached the brain from a classical physics perspective, treating it as a biological machine where neurons communicate through chemical and electrical signals. However, some researchers propose that the brain may function at a quantum level, utilizing principles from quantum mechanics, such as superposition, entanglement, and non-locality, to process information in ways that classical physics cannot explain. Could our thoughts, memories, and consciousness itself be influenced by quantum effects? In this chapter, we explore this possibility by examining the classical versus quantum models of the brain, the Penrose-Hameroff-Orcoa theory, the role of quantum coherence in cognition, and the controversial idea that memories might be stored non-locally. Classical versus quantum models of the brain, the classical model of brain function. For a long time, scientists have understood the brain using classical physics, the same rules that explain how cars move, how planets orbit, and how electrical circuits work. According to this model, the brain processes information like a complex computer, using electrical and chemical signals to send messages between its cells. The brain contains about 86 billion neurons, tiny cells that process and send information. Each neuron connects to thousands of others, forming a huge communication network. A neuron has three main parts: dendrites, which receive signals from other neurons, an axon, which sends signals, and axon terminals, which pass messages to the next neuron through small gaps called synapses. Neurons communicate using tiny electrical signals called action potentials, which work like flipping a switch to send a message. When a neuron receives enough input, it turns on and sends an electrical pulse down its axon. After sending the signal, the neuron quickly resets, ready to fire again. These signals travel incredibly fast, up to 120 meters per second, allowing the brain to react almost instantly to what's happening around us. Since neurons don't physically touch each other, they use chemical messengers called neurotransmitters to pass information across the tiny gap between them, called a synapse. When an action potential reaches the end of a neuron, it releases neurotransmitters into the synapse. These chemicals travel across the gap and attach to the next neuron, either exciting it to send its own action potential or inhibiting it to stop the signal. Once the signal is transmitted, the neurotransmitters are removed to clear the way for new messages. In this classical model, the brain functions like a biological circuit where neurons and neurotransmitters handle thinking, memory, emotions, and movement in a predictable way. This model successfully explains many aspects of cognition, from simple reflexes to complex decision-making. However, it struggles to explain phenomena like the binding problem. How do different brain regions integrate information to create a unified perception of reality? The hard problem of consciousness. How do electrical signals in the brain give rise to subjective experiences and self-awareness? Memory storage and retrieval. Where and how are memories stored? And how are they instantly accessed without searching through a physical storage system? Some researchers believe these mysteries may require a quantum explanation. The quantum model of brain function. Quantum mechanics governs the behavior of subatomic particles, where particles can exist in multiple states simultaneously, called superposition, be instantaneously connected across space, also known as entanglement, and exhibit probabilistic rather than deterministic behavior. Some scientists believe these quantum effects may be occurring inside the brain, influencing cognition and possibly even giving rise to consciousness itself. The idea of a quantum brain gained credibility when scientists discovered structures inside neurons that could theoretically support quantum processes. One of the most well-known quantum theories of consciousness is the orchestrated objective reduction theory, proposed by Roger Penrose and Stuart Hameroff. In the 1990s, physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed the orchestrated objective reduction, or OR, theory, suggesting that consciousness arises from quantum processes inside neurons rather than from classical neural activity alone. At the heart of this theory is the idea that quantum computations occur within microtubules, tiny, cylindrical protein structures found inside neurons. What are microtubules? Microtubules are structural components of cells providing shape and support to neurons. They play a key role in cell division, intracellular transport, and neuronal communication. Hameroff and Penrose proposed that microtubules could also function as quantum processors, using quantum coherence to integrate and process information across the brain. Microtubules are believed to play a crucial role in quantum consciousness through several key mechanisms. One of the most important concepts involved is quantum coherence. In simple terms, quantum coherence occurs when particles, such as electrons or photons, exist in multiple states at the same time, a phenomenon known as superposition. Normally, in classical physics, objects exist in only one definite state at a time, but in the quantum world, a system can be in many possible states simultaneously until it is observed or measured. Hameroff and Penrose suggested that microtubules inside neurons could sustain quantum coherence, meaning they could hold and process vast amounts of information in a way far beyond classical computation. If microtubules truly function in this manner, they could allow the brain to perform highly efficient and interconnected processing, like potentially explaining the depth and complexity of human thought. Another fascinating idea is quantum entanglement, which means that two or more particles can become instantly connected, no matter how far apart they are. If microtubules within different neurons are entangled, this could allow different parts of the brain to communicate instantly, providing a possible explanation for how we experience unified thoughts and rapid decision-making. Unlike classical neural transmission, which relies on chemical and electrical signals traveling between neurons, quantum entanglement could enable near-instantaneous information sharing across different brain regions. Penrose's theory, called objective reduction, OR, says that tiny structures in the brain called microtubules hold quantum states, meaning they can exist in multiple possibilities at the same time. But these states don't last forever. They eventually collapse into one final state because of a natural process in the universe. According to Penrose, this collapse is what creates consciousness. This means our awareness and thoughts don't just come from normal brain activity like signals between neurons. Instead, They happen when these quantum states collapse. Unlike regular physics, where everything follows strict rules, this collapse is unpredictable. Because of this, our brains don't work like computers that follow fixed instructions. Instead, we have free will and creativity, allowing us to think in new ways and make unique decisions. In simple terms, this theory suggests that consciousness isn't just a product of brain activity, it comes from deeper quantum processes, linking our minds to the fundamental nature of the universe. Let me try to explain this whole concept with a real-life example. Imagine you're sitting down at your piano, ready to create a new song. You might start by playing familiar chords or rhythms, but then, instead of just repeating what you've already heard or learned, something new emerges. You suddenly create a melody that feels fresh and original, something that doesn't come from any previous song or musical pattern you've ever played. It's not a predictable choice based on your past experiences, but a moment of true creativity. According to Penrose's theory, this creative moment arises because of quantum processes happening in the microtubules of your brain. These quantum processes allow for superposition, meaning multiple musical ideas exist at once in your mind. Then, when the quantum state collapses, a new, unpredictable idea emerges, one that couldn't have been foreseen based on your past knowledge. This moment of musical creation is the result of the collapse of quantum states in your brain, introducing creativity and originality that classical brain models can't explain. So, instead of simply choosing a melody from what you've learned, the quantum collapse allows your brain to generate something truly unique, something new that hasn't been thought of before. This is the kind of creative process that Penrose believes is driven by quantum mechanics, making it unpredictable and beyond deterministic brain activity. The role of quantum coherence in thought and perception. As we said earlier, quantum coherence is a phenomenon in which quantum states remain in a delicate balance, existing in multiple possibilities at the same time. In simple terms, it allows for parallel processing, where multiple outcomes can be considered simultaneously before collapsing into a definite state. In physics, this is a crucial property of quantum computers, which process information far more efficiently than classical computers by leveraging this ability. If the brain operates using quantum coherence, it could explain several fascinating aspects of human cognition that classical models struggle to fully account for. Parallel processing in the brain. One of the most remarkable abilities of the human brain is its capacity for parallel processing. Unlike traditional computers, which process one task at a time, or use limited multitasking, the brain can handle multiple streams of information simultaneously. For example, when you are walking through a busy street, your brain processes the movement of people, incoming sounds, the feel of the ground under your feet, and even your own thoughts, all at once. If quantum coherence is at play, it could mean that the brain, like a quantum computer, is performing multiple calculations at the same time before settling on an output. Instantaneous decision-making. Humans often make split-second decisions without consciously analyzing every possible outcome. For example, when a driver suddenly swerves to avoid an obstacle, there is no time for a slow, logical evaluation of all options. One possible explanation is that the brain maintains quantum coherence, where multiple possibilities, such as braking, swerving left, or swerving right, coexist for a brief moment. When this coherence collapses, the brain instantaneously selects a single action. This rapid decision-making process, which seems too fast for classical neural computation alone, could be a result of quantum coherence influencing neural activity. Unified perception, binding sensory inputs. Another mystery of human perception is how we experience the world as a unified whole. Different senses, sight, sound, touch, and smell, are processed by different parts of the brain, yet we perceive them as one cohesive experience. Classical neuroscience explains this through neural synchrony, but it doesn't fully address how all sensory inputs are seamlessly integrated in real time. Quantum coherence offers a potential solution by suggesting that these sensory experiences exist in a coherent state before collapsing into a single unified perception. This could explain why our consciousness experiences the world as an integrated whole, rather than as disconnected bits of information. Quantum processes in the brain. While these ideas are intriguing, the role of quantum coherence in the brain is still highly speculative. Some researchers propose that brainwaves, synaptic activity, and neurotransmitter interactions could be linked to quantum processes. Others argue that biological systems are too warm and noisy for quantum coherence to persist long enough to influence cognition. However, studies on microtubules and other cellular structures suggest that quantum effects might be more resilient than previously thought. If quantum coherence plays a role in cognition, it could revolutionize our understanding of how thoughts form, how decisions are made, and even how consciousness itself arises. However, more research is needed to confirm whether the brain truly harnesses quantum mechanics in this way. Stay tuned to our channel for more mind-boggling content on quantum mysteries.